Okay, so you should probably now see, all of you, the results of this question, and the right answer was C. So I had a number of people who did not answer it correctly. And so what I have decided to do is I gave as an exercise today, and I have assigned it until Friday. And I'm asking you to explain your answer to just the exercise that ended today. All right, so I say here the exercise for starting today until Friday when we have a lecture. I would like you to explain your answer. And it is here, now you can write it in words and so forth. I mean, write it in words. Explain to me why you came down to that decision. I wanna see how you thought about it. I will review your answers to give you the points for correctness, obviously, because I would like to see what you have explained, how you have explained your answer. And so please make sure that you do that. And we are going to discuss the results on Friday, but a number of you got it wrong. And it's extremely important because it's a very fundamental question on matching. So either you rushed into answering something, or there is a more fundamental problem. So we'll like to see. I would like to see exactly. Any questions about that?
So this time it's a short answer question.
It's an answer question. Explain your answer. That's how you should see it. And you have to write your response. Okay.
Professor, will you open the previous question as a review so we can see what the answer choices?
Yes, yes, of course. Open it, review. Yes.
So we need to put why we answered the way we did, or
yes, why you answer. No, I don't want you to correct anything. I want you to write why you answer the way you did.
Okay, and I was a little confused on this exercise, like because of a fourth wavelength open circuited stub, that's a parallel LC, but it can't be approximated as a parallel LC for filtering purposes, right?
A shunt quarter of a wavelength open circuited stub, what does it become? Becomes a short.
It doesn't, I remember in filtering, you can put
yes,
that.
You cannot put a short someplace. It can become an open or a short, but it's a combination. But if it is by itself, it says here the following: a shunt 1/4 of a wavelength opens a shunt. Okay, 1/4 of a wavelength open circuited stub cannot match any load to the transmission line. Because at that point, when I say 1/4 of a wavelength, I have already decided my frequency. It cannot be 1/4 of a wavelength for any frequency. So at that frequency, where it is 1/4 of a wavelength, creates a short, cannot match anything. A short is a short.
Okay.
Am I right?
Right.
Okay.
I guess
yes.
From a lump sum element perspective, I guess I was thinking back to when we were designing filters, and it's like, it just seemed like a very strong thing.
Short, it has to be a series LC in shunt configuration. But even if it's a series LC, when it is 1/4, I mean, a 1/4 of a wavelength shorted stub, open stub is a short, no matter how you want to see it. It's a short when it is 1/4 of a wavelength. It may not be a short if it's away from that, but at 1/4 of a wavelength is a short.
Well, Dr. Tetehi, I think this question is almost identical to one in the makeup assignment, but in that assignment, this one is correct. B is correct answer of one of the correct answers.
It's not exactly the same. I have changed it slightly. I have made some changes. And I'm suggesting, I don't want to negotiate this. Please think about it. That's why I ask you to think exactly what you're gonna tell me. And you have to explain how you're thinking about it. So I can have an opportunity, because it will be, unless you wanna, I would like to wait until we solve it later. I want you to see why your answer was not correct. Because I'm telling you, it's B is not correct.
Okay.
Excuse me, C, I'm sorry. C is correct as a statement, I'm sorry. It is it's a correct sentence, what I put there. And those who thought it was not correct, I'm explaining why. The difficulty in these statements is you have to read it carefully. You have to understand what it says, which is important, because most of the time students make mistakes in homework and especially exams because they don't read carefully, or they read something, they're under stress, they're under pressure, and then they miss something, and then the outcome is wrong, okay? A lot of times you can miss something and then you can spend a long time on something that is wrong, wrongly stated. So the thing about these exercises is that you have to read them carefully. You have to sit down and think. A lot of times I would sit down and draw something before I respond to it. I mean, you could put a stop that it's a quarter of a wavelength and is open, and see exactly when it's a quarter of a wavelength, how it looks at the input. At the input, it's going to look like a short at the frequency where it's a quarter of a wavelength. So at that point, it cannot match anything. It's going to short. Whatever load you have is going to short it. Okay? Any
Okay.
other questions? Is that correct? Is that clear? I mean,
Yes.
okay. Sit down and please do that. So I would like you to take the time and think about it. Don't take it because I just said so. I want you to see what the right answer is. Okay, so that is the exercise for next time. I would like you to look at your solutions. I mean, give me whatever explanation, but also I would like you in the process to understand if you have made a mistake too. All right, it's mostly for you to sit down and identify if you have made a mistake, why, and what did you think that maybe you have to correct next time. And if you have not made a mistake, again, you know, I don't, if you just, very few people will go here and just grab an answer and then leave. But if you don't understand why you went for this answer, I want you to explain also.
Okay.
Okay, all right, now let's move. Let's move to our example today. You will see so many of those. So this is yet another example. And I don't believe we started on this last time, did we? Can somebody tell me?
I don't think so.
I don't believe so. No,
Okay.
not Iggy. Yeah.
Perfect. I just want to make sure. Okay. I'm asking you also questions because a lot of times I don't want to feel like, well, let me see what happened here. A lot of times, if we don't have an interaction, I feel like I'm lecturing to myself. So it's not good. So that's why I'm asking you questions, because I would like us to stay connected. All right. Now I'm going here. So this is yet another example. the interesting thing here is you will see something different. I have added something. Before, I was asking you to, in the previous example, the question was, how do you design a low noise amplifier where you have to achieve some kind of noise and some kind of gain? Okay, and we showed how to do the noise circles, the gain circles, and see where they intersect, and then select the point. Now I'm changing it a little bit, and I say, well, what I would like you to do is to design a low noise amplifier, but in addition to having, and now you understand, all right? So I'm trying to design it for the best possible noise, the best possible gain for the lowest possible noise. And now I'm throwing something else into this whole thing. I'm saying, in addition now, what I would like you to do is to see whether you can make the input VSWR to be less than 1.5, okay? So what is the input VSWR? We will see it later, but just here to start the solution. If you remember, the low noise amplifier is made out of 3 sections. The transistor with the appropriate bias and so forth, the output matching network, and then of course the load here, and then the input matching network, and then here is the source. So practically your amplifier starts here and ends there. So this is your amplifier. All right, when I make it, that's what you see. So if I were to design this, and let's assume that it's a low noise amplifier, so I have an F minimum and an F, which is as close to minimum as possible, all right? So F is gonna be higher than F minimum, but low. So, and then I have a gain for this amplifier. We'll talk about the various gains again to remind you. So most of the time we're using this transducer gain, and we want this transducer gain to be as high as possible. So it's gonna always be below the G max, because this is the maximum possible you can have for this source and this load, but we wanna go as low as possible in F, as high as possible in G, okay? And usually what I said last time is if this is the range of values for F mean, that's your F axis, and this is your G below, so F axis here, G axis here, and let's assume this is my G max, and this is the G values. Usually what I see, and let me give it a different color here, just so, all right, let's do that here. And so we have the axis for G, okay. F goes from F minimum up, G goes from G max down. So as F goes like this, G goes like that. And every time we try to find one point here, one point where we are below G max, but not that much. We are above F min, but not as much, the optimum point between the two. But now I'm throwing to you something else. And here is the reason. If I take this amplifier, all right, I said, this is my amplifier. It's made out of 3 boxes: the transistor, and the input matching network, the output matching network. So practically, I will take this amplifier, now that I have designed it, and it's low noise, and I will connect it to my load and my source. Now, you know what from our project, for which I wanted to tell you, I'm gonna give you the last phase of your project for the LNA today. So to have it done by the second. Okay, in this one, this part here might not necessarily be a simple source. And this part there, here, might not necessarily be a simple load. What that means that on the source end, you may have another, like you remember how we put the low noise amplifier? Where do we place the low noise amplifier in a system? Do you remember? In a receiver. So we start with the antenna, and then where do we go?
Is it antenna, filter, LNA?
Exactly. So we go to a filter. You remember this description of a bandpass, or you can see it like this. And then we go to the LNA. And then where do we go from there?
Mixer.
Mixer. I mean, a simple thing, all right? So as you can see, my load is not a resistor, or is not something else, it's the mixer. So here, this is my load. And what is my source? My source is really the filter. This one is this one. All right. So that means that when I do this, and when I want to have a good gain and a minimum noise, at the same time, I cannot ignore the fact that I'm going to connect to two other components. Okay, going to a filter. What do I want to see when I go to a filter? Of course, I want to see a good filter performance, but I don't want to create high reflections here. Why is that? Because if I create high reflections there, I'm going to have less power going to the LNA. Okay? And I don't want to create also, even if it's less, this is less critical. At the output, I don't want to do that, because if I have any reflections here, smaller reflections from the mixer, those will linger here, and I'm going to lose a lot of power because of reflections, because of the back and forth. All right, every time the wave moves along a line, it loses its power into ohmic losses. All right, so, but as I said, the output is less critical than the input, because even your input, you lose power, you're going to have even less power to amplify, and your gain is not going to be good enough. So how do we define the requirement that this gamma here, which is the gamma practically right here, all right? How do we define this requirement that this gamma in is small? By a VSWR. That's how usually in circuits we define low reflection coefficient. Many times you will not see reflection when it comes to passive components, like when it comes to mostly passive components or other connectors and stuff, you're gonna see a VSWR. And how much is the VSWR? Do you remember?
1
Magnitude.
gamma divided by 1 minus gamma.
Okay. So to minimize gamma, if gamma goes to 0, your VSWR is 1. That's the optimal value. And as gamma goes away from 0, then your VSWR increases. All right, so the minimum VSWR is 1. And then it goes from there. Okay, having said that, that's just a reminder. Here, I'm asking you to make the input VSWR less than 1.5. This is a number, 1.5, all right? So from there, I know how much is going to be my reflection coefficient, the magnitude. So that 1.5, sometimes people may go to even more less, 1.3. Some other times may go to 1.1, depends, on how sensitive your system is to different things. 1.5 is kind of okay, it's not a great one, but it's not a bad one either. Like 2 and above, forget it. Nobody's gonna go for a VSWR that is 2. Too high of a reflection coefficient. Any questions so far? Okay. So at this point, let me move this up so we can move down. All right. One thing which we did not do last time when we started, remember that I outlined a number of steps for you? You remember that in the last example?
Yes.
Okay. How many steps did we have?
I want to say 7.
7.
Yes.
Yes. Now, of course, when you start and when we start the review on Monday, I'm going to give you I'm going to try to put everything together because I know now it's scattered in your mind everywhere. So we'll try to put things together when it comes to low noise amplifiers. So I will outline all of the steps, even the small ones. But a lot of times, we are not counting every single step. You count only the big ones. In any case, one step that we missed last time was the stability check, because the particular amplifier we got was unconditionally stable. Okay, so knowing that it was unconditionally stable, we did not do a stability check. However, it's all, unless the maker tells you that this amplifier has been designed to be unconditionally stable. And if you remember, there are some makers of transistors that will give you K and delta. And they will tell you, for example, that this transistor in this frequency range is unconditionally stable, stable. So in this case, you're not going to test it. But if they don't give you this information, the first thing that you have to do, step number 1, is to find whether it is unconditionally or conditionally stable. And here we have 2 parameters, K and delta, or you can use mu only. I decided to go for K and delta because eventually we're going to use the values of K and delta. All right, so what I did, I took the expression for delta, which you will find here. And then I found that delta is less than 1, maximum of delta is less than 1, the magnitude. And then I took K. And then we found that the magnitude of K is less than 1, 2. And that is a problem, because when the magnitude of K becomes less than 1, then we understand that transistor is conditionally stable. So what happens if your transistor is conditionally stable? You have to find what are the instability regions before you start doing anything. Because if you cannot find a reasonable instability region, if you find that your instability region takes the majority of the Smith chart, then you have a bad transistor for your application. I would tell you, unless they tell you this is the last transistor that we have left on this earth, I would not go for a transistor that gives you a very small section on the Smith chart that where you have stability, where you have possible stability, because you have to design it in that section, all right, to be stable. But I was going to be looking for transistors that give you enough section of the Smith chart to do your other designs, because if they give you a sliver of the Smith chart to stabilize it, and then having on this in this sliver to also do all of the other things between the noise circles, the gain circles, plus the VSWR that I have asked you right now, you're not going to be able to do it. So you're looking for a different transistor. So let's see, before we decide whether this transistor is good or not for our application, let's try to find what is the stability region. We have to find both the output stability region circles and the input stability circles. All right, that you have seen before, and I am placing them here again, their formulas from our previous lectures. And then I have also here calculated it. Now look at this. Isabel has a huge value in magnitude, 903. So 903, since we have only from 0 to 1 to measure, here we have only this one to measure magnitude. From 0 to 9 is going to go out of your paper, if you use paper, and out of my screen of the computer. Okay, so obviously I'm not going to try to find the center of CL somewhere in free space, all right, somewhere in the air, but I will try to do something simpler. So what I'm doing, how I'm thinking here. Look at 903.03 and look at the radius, which is 9.9. Instead of me trying to find the center somewhere, use 10 different papers, one expanded next to the other to find where 9 is, and then draw a huge circle, not even your compass will be able to do it. I look at the difference between 9.03 and 9.9. For the following reason, and now I'm going to include to explain to you why I did this, why I thought that way. I'm going to include a page here. Okay, if this is my Smith chart, now let's assume that my Smith chart is this small. And I find, first of all, we need to remember that both Isabel and Isabes have the phase of this entity you see in the numerator. So they are on, the Isabel has a phase of minus 36 degrees, and Isabes has a phase of 130.7. Okay, and now I'm trying to find both. Let me see what I did first. The input, all right? So let me see. And in fact, you remember that there is a minus 36. So I will find, first of all, the input stability circles, the green ones, and then you can do the output the same way. So I'm going to the input stability circles, and you see that my radius here is 3.68, and the phase is minus 130.7. So I know that the phase, regardless of all of these circles, will be the same, and the radius is going to change, obviously, depending on what kind of, the circle is gonna define a range, but the direction of where the center of the circle is gonna be is defined by the phase. So if I go on the Smith chart and I measure here the phase, and it's gonna be somewhere here, so I know that even if I don't see how far it is from the Smith chart, because the Smith chart has radius of 1, and I have a radius of 3.68. So I know it's 1, 2, 3, that my center is going to be somewhere here. Okay. And then, so from the center, to here is going to be 3.68. Okay, and I know that this is the center, CS. And then let me now find 2.77. The radius of the Smith chart is 1. So from here to there is going to be 3.68 minus 1, which is 2.68. But the radius, R sub S, is 2.77. So if I were to draw this circle, let me do it green, it's going to look like this. And why is it going to look like this? Because the distance between the end of the Smith chart to the center, the distance between the end of the Smith chart, which is right on this blue line here, which is somewhere here, and the point where the circle intersects the Smith chart is very small, because the radius is 2.77. The radius is 2.77 minus 2.68. So practically, how much do you have? 0.09. So that is this small difference here. And if you are to plot this, it looks like that. You see this green area? Excuse me, 1 second. All right. This area here, the green that you see, let me see if I can, you see this green area that says input instability region? This is the only, this little sliver here is the only instability region. And because the magnitude of S22 is less than 1, the rest of the Smith chart is the stability. You see that?
Question.
Yes.
Is the green area, is that approximation, or you know the exact area?
I know it because I got this. It's not an approximation. I mean, it's close enough. I cannot tell you that is exact because, and I have to explain it to others as well. When I'm doing these things, I'm doing them on notability. I don't have a compass, and I don't have an electronic compass, and I don't have an electronic ruler. So I'm trying the best I can to come as closest when I represent these values to the real thing, but I cannot tell you that it's going to be exact. All right. Is that what you're asking?
Yeah, because the way you said we should draw the input instability region circle, it wasn't accurate, like to really plot it, because
where was the error?
I mean, how can we draw the 0.009 line inside the Smith chart?
So you are asking about what?
The mutual area between the Smith chart and the
How I
green.
did it. I'll tell you how I did my approximation.
Okay.
All right. This is engineering now. Engineers need to be able to work without MATLAB available and without other. I mean, I was trained like that because when I was in your age, we did not have MATLAB. We had some flimsy calculators that were doing 4 as addition, subtraction, multiplication, and nothing else. And we had a ruler, which I never used. So we learned, and that was an amazing engineering capability, all right, to think on how to do things simpler. So here is what I thought. Here is what I'm thinking. If you think that I am an observer here in this area, think of this, oops. Let me draw this circle. I'll do it. A good engineer, if you close somebody in a room without a computer, should be able to design something. That's the, the bottom line. But let's assume that now this is a circle. I see that. I see the circle, all right? What happens if I come very close to the circle? This. What do I almost see if I come even much closer? Let me grow the circle a little bit more. Let me see. Here,
Straight line.
book, circle. So what happens if I come much closer? Ah. What do I see?
Straight line. Straight line.
A straight line. So what did I do? I went there and I measured the distance between this point here. I will put it here, this point here. You see that point that I'm putting my pen?
Yes, I think so. Yeah.
And this point here, I measured this distance, the blue, to be 0.07. And that's how I found it. And I drew a straight line.
Okay.
And it's very accurate, as a matter of fact. Considering, you know, how we do the designs. And I did the same with the other one, even more, because the other one is 9 point something. Okay. So I found in both cases, that was important. I found that I have the majority of space on the Smith chart to be able to do my design. And that was critical. So now I'm going to continue. I know that in the red area here and in the green area here, I cannot select a value in those two areas, because if I select a value of my gamma S or gamma L in any of these areas, the gamma L in the pink, the gamma S in the green, then I know that I'm going to have a problem. Okay. So after now I did this, where do I go first? I go to design the noise circles. I'm going to work with the noise, first of all. And first noise. I mean, you couldn't start with something else, all right? You don't have to always start with noise. You could start with gain. You could start with the VSWR, as you will see. I mean, when people give you more than one requirements, there is not a particular order, because at the end, you have to put all of the circles and see where they intersect. So it does not matter whether you start with noise, you could start with gain. I decided to start with the noise circles. Okay, so I put down the expressions for the noise circles. And I did a small table according to that. And since CISA-BEF is gamma optimum that was given to us, the phase for CISA-BEF is the same for every F noise. And in that particular case, I changed N, the N coefficient, which goes from 0, and then small values, but I have not put the N value here. I just did it faster, right? I calculated faster, and I did not look at this many values for F. I looked at 2, 1.3, 1.5, and 2. All right. Now, I drew these circles. Of course, gamma optimum, and how much was gamma optimum? Gamma optimum was 0.41, all right, at minus 150. And that gives an F minimum of 1.2 dBs. So this is 1 point, all right? If you select the gamma S as your gamma optimum, then you get as F, you get your minimum. But I'm not gonna go and select a point because I don't know where the gain circles are. I mean, I have other considerations, all right? So I want all of the circles that I could put in there. And I drew here my noise circles the way they correspond to, I put the gamma optimum to see it at the center, and then the smallest circle, blue circle, is 1.3 dBs. And let me put here dBs for noise. The other is 1.5 dBs, and the other is 2 dBs. And from experience, and usually from the requirements of the system, people told you, you know what, the 1.5 dBs is good. You know, if you can create a system that has a noise of 1.5 dBs, then I think you're perfect. So that's why I keep my eyes on the 1.5 dB circle. Okay, any questions so far before I continue? All right, now let's talk about the VSWR next, all right? Because now they have put one more condition that says that you're on the input port, as I showed it to you before, you cannot have a very high reflection because I have a filter before that. And if you have a high reflection, all of the power that comes through the filter, I'm gonna lose a lot of it. And I don't wanna do that. Okay, so we understand that. How are we going to deal with this concept? Okay, now look at this figure that I have here. And what I have tried to do as I explained to you before, if you assume that this source here is your filter, I look at the reflection coefficient right in between the filter and my amplifier, but looking towards the amplifier, because I cannot design the filter. That's not my job. Somebody else is going to do it. Hopefully they will do it well. I need to do my amplifier well. And I need to make sure that this gamma in at A, which I have it to just separate it from the other gamma in that I have inside. All right, so I put an A to think that is on the input port, B is on the output port. This one is connected with VSWR, and you can prove that this gamma in, and in fact, I wanted to put the proof here, but I ended up spending more time solving the rest of the problem. So I will not have I don't have the proof here for that, but either you can prove it yourself or I will provide it to you next time, the proof for this expression. So let me move this. So you can prove this. All right. And we know from the VSWR definition that gamma in and VSWR is given by that. So if I know the maximum VSWR that I can accommodate, which is 1.5, then I can find the highest value in magnitude for gamma in alpha. All right. So now what am I going to do next? Well, what normally we do with everything else. You can prove, and I will give them to you because the expressions for what I'm going to show you next are fairly extensive to go through these proofs, and I don't want you to prove anything there. We're going to design also circles. What you find out is that your VSWR, in terms of your gamma S, is also on a circle, all right? Because what you saw from here, look at this. What you found from here is that your gamma in alpha, and therefore your VSWR alpha, are a function of gamma S, okay? They are a function of gamma S. And therefore, for different values of gamma S, then you will have different values for VSWR, but then you find out that all of these gamma S values that correspond to a particular VSWR are on circles. And these circles have, and they're called the constant VSWR circle. And of course, they are the input. You see VI. So C sub VI means the center of the constant VSWR circles in the input port. and is given by expression 10, by this one. So this is where all of the centers are. And what do you see? That these centers have the phase of the complex conjugate of gamma in. Okay, gamma in, not gamma in alpha, but gamma in. And then also you have the radius of each one of these circles that is given by this expression 11. Okay, and gamma in alpha is determined by the VSWR. All right. Now, is it not true that my gamma in is really my gamma S? Do you agree with this? Is it true that my gamma in is really nothing else but my gamma S? What is the relationship that we have established between gamma in and gamma S?
Gamma S is the complex conjugate of gamma N?
Yes, and for maximum gain. Okay, so practically my gamma in and gamma S, if gamma S, for example, if my gamma in changes and I assume that gamma in is gamma S complex conjugate, in reality, yes, I have gamma S in there. And so when I solve these equations for constant, for the circles, what I have as gamma in reality, they give me a value for gamma S. And I will look only at these circles, only at the input constant VSWR circles. Why? Because it's only there, it's only the front end, my front matching network that is affected by the noise. Okay, so I'm not gonna look both at the pink and the green circles. I'm gonna look only in the front ones because first of all, my noise is only impacting the front, and the consideration I have about VSWR is at the front on the source side. So these two conditions about VSWR and about low noise really both determine an appropriate value for gamma S. Okay, so now I go here and I put the one circle that gives me a VSWR which is equal to 1.5. Why did I not draw all of the other circles? Because anything inside that circle is going to have any value inside the circle is going to provide for gamma S is going to provide a VSWR that is less, at most equal to 1.5 at the input port. Okay, so really for VSWR, I need one circle. Since I have decided I want it to be less or equal to 1.5. And I compute these circles from this one, from here. Okay. All right, now I found them. So what I have here is that up to, what I found here is the following, that I have a small section, everything that is inside the purple circle or the pink circle, all of these points here, I can select one point that it can get me, I don't know. Okay, sorry. All the points here, I can get any point. Somebody could tell me, well, I could go and even be better than 1.3. If I go, say, for example, here, if I go here, all right. If I go here, then I can go even better than 1.3. If I can go here, I can be between 1.3 and 1.5. you know, and then so on. But so practically, I know that I have to be better than 1.5. So somebody can tell me all of this part is appropriate. Okay, which is true if the only thing that I needed to do is to get under control my noise and to have a VSWR that is less or equal to 1.5. But the bottom line is that we also have considerations about the gain, because you cannot go to the lowest noise, have a good VSWR, and then have a gain which is 1. I mean, you know, why would you put an amplifier in there if your gain is very small? So now I come back and I say, now I want also my gain to be close to 10 dBs. In addition to, so from this region that I have shaded here, I want to find the points that will give me also a gain which is better than or a minimum gain of 10 dBs. So what would I have to do next is to develop the gain circles, which we are going to do next time. But, and I would like to just briefly look at the gain circles. We've done them before, but also next time I will remind you all the various gains, the definitions and so forth, so we can put all of this together somehow. So I want to take you back to some things we have seen before. In any case, so that's where we are today. And do you have any questions? Any questions?
Yeah, can you go back up to where you found the stability circles?
There.
Where the equations for it are.
Okay. There.
So it says the center is 9.03 and the radius is 9.9.
That's
so
for the output, the red one.
Wouldn't that result in or circle ultimately being across the center of the Smith chart?
This one, the red one.
Yes, correct. But if I'm reading that correctly, then the center or the radius of the circle is bigger than the distance from the center to the center of the Smith chart. Is that correct?
Yes.
So then wouldn't that stability circle be on the other side of the center of the Smith chart?
Because is bigger than because the radius is okay, so it's minus 36. Okay, and where is minus? You remember CN? Let me go back here. Is minus 36. Where is minus 36? It's down here. So I go down there, that direction, not the other one, to find the center of this circle.
Oh, okay. Yeah, I see it now. Sorry, I got the.
No, that's okay. That's all right. No, that's a good question. Yeah. And so it goes there. Okay. Yes. All right. So I have office hours, and we have office hours in half an hour and or so, and then so I'll see you there, those who want to come. Okay, see you later.